So what I decided to talk is actually related to what I teach also at PG level, and so one special course I offer at Plasma Basics in Plasma Physics and its application, and then also it's a part of my research work, as you have noticed while I was being introduced. So the topic I have chosen today is emission and absorption spectroscopy based diagnostic for low temperature non-equilibrium plasma. So we will try to look at two aspects here. One is what diagnostic scheme which can be employed for low temperature non-equilibrium plasma. And these are different class of plasma which we know. Whenever the plasma word comes or someone spoke this word, we generally try to refer it either some kind of atmosphere where you have very hot plasma, and or you sometimes people relate it directly to plasma TB. So I'm just want to tell you that this is a different class of plasma which basically emerges in last few decades, and because of its very interesting application, and we will know what kind of application these plasma can be employed and why it is so important to diagnose these plasmas. So more, and as mentioned, I belong from IIT Tirupati Physics Department. This is my email ID. So if anyone wants to have any questions or any discussion after this talk, please feel free to contact me on this email ID. One another thing is the most of the things which I will be discussing in the talk has been taken from these three references. So all of the topics or further details can be accessible from these references. So let's go ahead. Let me start with introducing what is the plasma. So mostly we are familiar with three state of matters. We call it solid, liquid, and gaseous. And a class of gas. So if you want to make a transition from solid to liquid or liquid to gas, there are different processes we can highlight. But in the bottom of this, we need to supply energy. So if you want to make a phase transition from solid to liquid, you need to supply energy, and then similarly to gas. What if you are still continuing to adding the energy to gaseous medium? Then there is a possibility that you ionize the gas. And when you start the ionizing the gas, then what will happen? The medium start having neutral particles, ionized particle, positively ionized particle, and electrons. So this is what we call ionized state of matter. Now, all ionized state of matter doesn't constitute a real plasma. So sometimes it's confusing. So because in order to represent any medium as a state of matter, we need to define some macroscopic properties to that matter or that state of matter. So in the case of plasma, until the plasma sustains some kind of a collective behavior, we cannot call all ionized as a plasma. So if you start putting the energy inside the medium, and if they attain sufficient of amount of energy, means ionization, then there is a possibility that your plasma can change to the ionized gas can change to the plasma state. Now, how do we know that it has reached? So there are various parameters through which one can know, and one just for refreshing, we know that the Coulomb's law is 1 upon R law, and as soon as we start having a core shell, then there will be a screening factor, and this potential got screened out. And we can define this screening through one length, which we call Debye length. So this Debye length is actually basically depend upon the density of charge density of the system, of average energy of the particle constituent. So if the plasma dimension is much larger than this Debye length, then what will happen? You can have a quasi-neutral environment. When I say quasi-neutral environment, means plasma simultaneously contain positive and negative charge in such a way that from outside is a neutral body, but inside it is having both positive and neutral charge, and it can also respond to external fields in a collective behavior, and that can happen if you have plasma dimension which is much greater than the Debye length. So in that case, we will achieve the plasma. Now, in order to define this state of matters, we need some parameters to define, and there are many parameters, but at least these three parameters are very important. So one we call electron temperature. As I mentioned that this plasma contains two kind of a particle. We can divide in a based on the mass. One is electron, which is much lighter mass particles, and then there are ions and neutrals, which we can think of they are almost of a similar mass if we consider a weakly ionized single ionized plasma. Now the average energy of the electron is basically, since it's a system, so we define it through some energy distribution, and the average energy of the distribution will define the electron temperature. So when I say electron temperature of plasma, what I really mean is the average energy of the electrons inside that plasma. And the popular unit to define the electron temperature, which is
Correct.
popular in this field, is 1 electron or electron volt. So if I say 1 electron volt, it is almost like 11,604 Kelvin kind of a temperature. Then the other parameter is electron density. What is the density? And then similarly, we can also define the average energy of heavy mass particles. Generally, we can call it gas and ion temperature. So when I say diagnostic of plasma, what I really mean to know the information of these key plasma parameters, either in a fundamental point of view when plasma is not being applied to any application, or in an applied sense when I'm applying this plasma medium for any specific application. During the processes, I want to know how the energy and the density of various constituent of plasma changes, because these changes reflects how the radicals or the reactive chemical species that is being formed by plasma behaves. So in order to see how the application will happen, or in order to optimize the application, we need the information of these parameters. Okay, now the next thing which we need to know before we go more on this diagnostic technique is there are different class of plasmas, and we can classify them based on the key parameters that I mentioned, which is mainly the T I'm referring as electron temperature, Ti I'm referring as ion temperature, and Tc I'm referring gas temperature. So there are two broad category we can do. One is what we call low temperature plasma. Another one is high temperature plasma. So high temperature plasma is normally the temperature can be much higher than 10 to the power 5 Kelvin. But another important point which you should notice here, that in this case, the ion and gas and the electron temperature, the all constituent lighter mass and heavier mass, they almost achieve equilibrium, and the species temperature are equal. So this called a high temperature plasma. But if you see the non-thermal plasma category, which is actually the interest of today's lecture, here we see a very different kind of a non-equilibrium nature. So you notice that TE is much higher than heavier mass particles. So what I'm trying to tell you here is that it is possible, since plasma contains a very varying mass particle where electron has almost much lighter particles, so they get thermalized much faster. Then ion-ion collisions or ion atom collisions, they thermalize themselves at a different temperature, which is of course much lesser than the electron, because its one response is much faster, its mobility is much higher compared to other species. So they attain a very high temperature. Now, how to move from low temperature to high temperature plasma? If you don't control the electron ion or electron atom collisions, which we call gas heating, if this process is also continuing happening, if you allow this process to happen, then what will happen? The electron will also effectively start transferring energy to gas molecule or heavy particles, and then it'll start reaching towards from low temperature to high temperature plasma. But we want to be in this regime, in this non-equilibrium regime, and the reason will be very clear to you just in a few minutes. There are different plasma category. I will discuss in detail what are different plasma category, but we will restrict ourselves to non-thermal plasmas. In this case, they are sometimes also called as low temperature plasmas. And among these low temperature plasmas, my main interest is to discuss today's atmospheric pressure plasma. Why people are more interested in atmospheric pressure plasma? The reason is very clear, because they don't require any kind of vacuum pumping. So it is very suitable for industrial scale processing, because industry doesn't want to have processing where you have batch processing. Because if someone can offer the solution which has a continuous processing, no vacuum required, then they are very happy, because it can basically help them to adopt that technology. So there is a good interest in low temperature plasma, and there is a further commercial scale interest for atmospheric pressure plasma. Now there are challenges in doing in atmospheric pressure, but over the time there has been many schemes developed. So if you see here, what I'm plotting in this is an electron density, and then I'm plotting the gas temperature. So you notice there is a very small region here where I can control the temperature. 300 Kelvin, I'm calling it a room temperature, but if I'm keeping my temperature from 300 to 500, I can form some kind of a plasma discharge or plasma, then that can basically be maintain their temperature at room temperature, but their electron density and electron temperature can be very high. So in principle, what I'm telling you, that you can touch the plasma by your hand since it's at room temperature, but its electron temperature and electron density is very high, so that whatever the required processing you need, because you need energetic particle to do the processing, that can be produced. Now, what is the challenge to get these plasmas? Why it's not so easy to get a low temperature plasmas at atmospheric pressure? So the reason is, okay, before we go to that reason, I just want to briefly tell what are these terminology. So if you see the literature, you will notice that there are different kind of terms people use, like glow discharge, normal glow discharge, abnormal glow discharge, arc discharge, Townsend discharge. Now, all these classification of plasmas can be done based on the IV characteristics. So what I'm telling you, you have a, let's say, some vacuum chamber, you created some low pressure, then you put an electrode, then you apply a field, either either time dependent or time independent field. And then you start recording the IV characteristic of this plasma. So you start putting, let's say you start increasing the voltage, and you will start recording the current. So what you will find that initially there will be some background ionization, mainly because there is some cosmic electrons will be present, so they will be drifted. And after that, at the C point, you will notice that there will be a exponential growth in the current, and that's what we call Townsend region. We haven't reached the breakdown yet, but since this is where your electron gets sufficient energy and they can start ionizing. So it's like a kind of a exponential ionization in the plasma, in the medium. And that you see that this variation in the current, if you increase this much voltage, the corresponding current increase is very high. So it's kind of a exponential increase in the current. Then at some point you will reach breakdown. So breakdown, as soon as you reach breakdown, there is a tremendous amount of charge production. Now, if you don't control this amount production, then you simply move very fast from here to here arc resume, which we normally see. If you take two wires, a normal experiment you can do, you take two wires and you just put in a air and you bring him close, and at some point you'll start seeing some arc. And that is arc is a kind of a thermal, because you might have noticed also there is a lot of heat energy you can sense also while this arc is happening. And it's uncontrolled. We don't want this, because when you have arc resume, for some application it might be useful, but the kind of application I'm looking, the arc resume generally we want to avoid. So we don't want the transition from here to here happen so suddenly. Now, how to control that? In order to control that, what I need to introduce some load in my circuit. And while introducing this load line, I can control the resume, the transfer from here to here, from a Townsend resume followed by normal glow and the urbanara glow to the arc regime. Now, in this case, in this breakdown voltage regime, you might have noticed that here there is almost a flat regime. This flat regime is kind of a very, very interesting thing. If we can sustain this regime, then we can have kind of a, even at atmospheric pressure plasma, we can have something which can be homogeneous and can also be expand to the full area of electrodes. So your current density will be like the plasma will be seeing the throughout the volume of electrode. So this is where we need to achieve, but the number of or the range of experimental conditions is very limited, because this is a very fast, you can very fast move to the arc, you can do that arc transition. But over the years, people have bring many techniques. I will not describe all, but at least the major one which people uses normally. But before we go, there is another thing which we learn like from Paschen breakdown curve. So if you notice that whenever you have an electrode and you have a dielectric medium and you want to achieve the, let's say you put even in, if you put in air, which is work as a dielectric, you start seeing the arc only after some time. And if you maintain the pressure, if you take two variable, pressure and distance between these arc, then you will notice that the breakdown voltage is basically function of these two variables. It depends upon the pressure and the distance of, and if you have, let's say you maintain the pressure, then there will be an optimum point. If you suitably arrange the pressure and the distance between the electrode, then you can achieve the breakdown voltage. However, if let's say I start increasing the pressure, so I'm moving from millitorr to torr, which means I'm moving from low pressure plasma to atmospheric pressure plasma, the price I need to pay is, in order to sustain the plasma, let's say in low pressure, I can put my electrodes, let's say for 10 centimeter, I have to reduce. Because if I'm not reducing my electrode, then there is no possibility that I can sustain a stable plasma. There will be a lot of instability in the plasma. So as I'm reaching to atmospheric pressure, I'm limited with the condition that I have to suitably reduce my gap. And at a certain suitable gap, I may be able to reach what we call kind of a homogeneous plasma, which basically comprises the full area of electrode. Now the trick, what should we do and in order to sustain such plasmas? So here there is another example which I just want to mention. So let's say you have this pressure varying in this direction and you have temperature varying. This is a gas temperature. If I write TE, then it's electron temperature. Now, what will happen if you are moving the pressure, let's say from here to here, the expectation is as you move the pressure, the neutral density of atoms inside that medium will also increase. So you increase the pressure, which will increase the neutral particle density. We can see it through standard gas law. Then the collisions between electron and atom or ions will also increase. So the collision between different massive species will also enhance. And this enhancement will effectively allow the transfer between the electron. And so you have a non-equilibrium region where TE was much, much greater than TG, which we call low temperature plasmas. But then as soon as you start increasing the pressure, what you observe that there's an effective transfer of energy from electrons to atom or let's say ion, and then you will reach. So this is where I'm reaching to what I called high temperature plasma or equilibrium plasma, where your TE and TG almost now the same. But the challenge is, how can I maintain this non-equilibrium region, but at a higher pressure? So in order to do this, there are a few techniques, and one very popular technique is, so let's say if I'm applying a signal, which is a sinusoidal signal. So I know that when I put, so let's say this is my one electrode, this is my second electrode, and I put, so at this point, I'm achieving the breakdown. So as soon I achieve the breakdown, what will happen? There will be avalanches of electrons. There will be a lot of flow of electrons. So I need to control this breakdown. So the one way I can control the breakdown by coating these electrodes with some dielectric. This can happen at one electrode. This can also happen on both the electrodes. So I'm introducing one dielectric. So what happens as soon as you have a breakdown, the charge flow, since there is a dielectric, so you start storing the charge, and then there will be a reverse direction field, which will reduce the effect of this applied field, which sometimes we call it as a memory effect also. So this will reduce the effect of this this applied field, and your discharge will distinguish. So rather than having the full cycle, it was supposed to have the breakdown up to this region, but by using this dielectric surface, we can control the region where only the breakdown region. Now, if we control the breakdown region, we can control the gas heating, and we can also basically maintain the non-thermal nature of the plasma at atmospheric pressure. So this is one of the technique, so which is normally or very popularly known as a dielectric barrier discharge. Now, this is only one configuration I have shown to you. Over the years, using this similar concept, people have developed many different kind of a geometry. For example, rather than using plane, people can also use, let's say you have a circular electrode, and then you have a concentric outer circular electrode, and you are producing the discharge between. So based on their applications and the interest, the concepts can be extended to various geometries, but the whole idea, basic idea, will remain the same. The another very interesting thing on which I'm currently working is what we call plasma jet. So plasma jet, let's say you take tube, and you are injecting some gas. Okay, now you put some electrode. Now there are various configurations for this, but I'm defining a very simple one. So you put the electrode, and then you apply your electrical signal to this. So what will happen? Your discharge will create here in this region, but since there is a gas flow, so you are injecting this discharge to the outer region. You can see here this discharge is coming. So this is kind of a post discharge. This is not active discharge. It is drifted to the outer region by using the gas flow rate. So these species has sometimes, so active discharge is in this region, but if you use suitably the gas flow rate, then you can extend this plasma region to the outer side, and that's why it's called also jet. But the advantage of this jet is, since it's a kind of a post discharge, so we can easily control the temperature. So we have reactive species in this region, and we also have the kind of a non-thermal nature in the plasma. So it's very much kind of a different scheme. Another one people also use, what they do, as I mentioned, you need to control the breakdown. So one another way is, let's say, rather than sending sinusoidal signal, I can send the signal, which is, this is very popular, nanosecond pulse discharge. So they send the signal, which is of the duration of nanosecond pulse. So the discharge happens for a very small, this is the same concept as DPD, but here they don't put the dielectric. The reason why they want to avoid the dielectric is, sometimes if you don't control it properly, then there is an erosion with the dielectric also, and that can influence the processing. You don't want the material from the processing in that, and you want to avoid the dielectric on your electrode. In that case, you can use at suitable time duration pulsed electrical signal, and you can produce such kind of a discharge. Now, before we move further, there is another thing which I would like to mention. What is this? Let's see here. So these all plasmas are also called as non-equilibrium plasmas. The reason is, in all these plasmas, they don't achieve thermodynamic equilibrium. And when I mean by thermodynamic equilibrium, so we basically can say, if let's say the radiation which is coming from the plasma follows the Planck's law, and the distribution of ionized state, or let's say neutral state following the Saha-Boltzmann equilibrium or Boltzmann equilibrium, or distribution of velocity is following the Maxwellian distribution, if all these is following or can be expressed through these things, then we can say, okay, plasma is in a complete thermodynamic equilibrium. But this never happened. In no laboratory plasma, it is possible to achieve the thermodynamic equilibrium. One simple way we can understand, as soon as you produce the plasma in any chamber, the radiation escape outside this plasma. So you will never have the kind of a environment where there is a backward process, which is, we can say, photo absorption, which can balance this emission of photon. So this process, this will never be in equilibrium. So a radiation always escape very fast. There is very less absorption. And that is why there will no equilibrium we can have that we can define through Planck radiation. Now, in the case of this, the states, now we can have the either distribution between neutral state or same ionic state, or we can have distribution between, let's say this is my P+1 state, ion state, and this is P, if I am having distribution between these two. So there is a possibility, still there is a possibility that we are not having complete distribution, complete thermodynamic equilibrium, but there is a possibility that we may still achieve equilibrium, which is electron-induced equilibrium, means we can define the state population distribution using Boltzmann law, or between the ionic state using the Saha equilibrium. So if such thing is exist in that, then we can say, okay, we don't have complete thermodynamic equilibrium, but we have something what we call local thermal equilibrium. Sometimes there is another word, if you achieve the equilibrium between the specific states, not the complete state, but only specific state, then you can also call this LT as partial local thermal equilibrium. So all these terminology being used, but the idea here is that you're not having the complete thermodynamic equilibrium in your plasma, but there is a possibility. Now, when this possibility can be possible, like what is there a way we can know whether the plasma will be in thermodynamic equilibrium or in LT or not? So yes, there are some theoretical calculations, and one of the one which decide what we call Meek criteria. So we need electron density. So there is a critical electron density, and that is of course linked with the plasma property, but one can determine the electron density, critical electron density. Beyond that, if your plasma having more than this electron density, then it is expected that your plasma is in local thermal equilibrium. But there are other ways also to know, I mean experimentally. Okay, so before we go, I would be now try to focus on one kind of a plasma among these low temperature atmospheric pressure plasmas, which we call plasma jet. The reason is because these plasmas has been utilized in various applications. You can see they have been used in, there are actually review also. One can go through it. And you will notice that over at least last 2 decades, there is a significant large amount of application for these plasma jets have been emerged. And also, in most of the cases, they have been emerged in something which we call noble areas like food processing, environmental application, material processing, biomedical application also. And especially in Europe, there are some countries where they also got permissions to do plasma treatment on patients, like active medical technology. This permission has not been yet given in India. But in Europe, some places they have already started doing the medical trials using the plasma jet. Now, why this plasma jet is so or any plasma is so much of interest? Because what happens, these plasmas produces these species. This we can categorize in a reactive chemical species. And we need the in situ production of these chemical species. So there are multiple ways to produce these chemical species. One, we can use chemical agent, active chemical agent, and we can produce this by a different process. However, in case of plasma, these species can be produced without using any external chemical agent. So you don't actually require any external chemical agent. So what they do, if let's say you have an ambient air, so your nitrogen and oxygen species are present, And since we have energetic electron, so this, when the plasma is in active region, it can produce all these nitrogen or oxygen based reactive species very effectively. The question is, or the challenge is, you need to produce good amount of reactive species so that you can achieve the desired application. Let's say you target one application, you need to produce good amount of reactive species, chemical species. However, you also need to maintain the non-thermal nature of plasma. Because let's say if you want to do biomedical application, you want to apply the plasma jet for wound healing, you cannot use a thermal plasma because it will also disturb the living cells. So we have to be very careful. And if the plasma has to be scaled in such novel application, then this aspect is very crucial. It has to be addressed before it can reach to the final technology, final TRL. There are some other applications. I'm just referring this so that if someone wants, they can go through these review articles. If you type on Google, you will find multiple such applications on plasma. You can easily do a literature survey. So I'm just passing this. This is the plasma which we have developed at IIT Tirupati. It's working fine. So you, as you can see, there is a finger. So we are maintaining the non-thermal nature. So you can touch the plasma also. Now, this is a most important part. So what we understand, we can have various designs of plasma jet. We can use various signal of plasma jet, like we can change the geometry, position of electrodes, frequency, voltage, current, gas composition. But how these changes are affecting my electron temperature or basic plasma parameters, because that basic plasma parameters will affect the production of reactive species. Now, how do I establish this link so that I can achieve the target? And the way we can achieve this is by using the by using the diagnostic. So we need to perform the diagnostic so that there could be a link between the external conditions, external operating condition, and the final outcome of the target. So we will go step by step on this. Now, there are many techniques that are available, and among them, the popular one can be categorized into one we call electrical approaches. Another one is called spectroscopic approaches. Electrical approaches is like where you put up something like a wire kind of a thing, which we call probe, and then you diagnose. But the problem using these electrical approaches, especially for this low temperature atmospheric pressure plasma, is this: because this is an active diagnostic approach. Active means when you introduce the wire or probe in the plasma, it disturbs the plasma. So the trick is, if you have a large volume plasma and you are putting the probe, it's fine because it has some local effect and we can compensate. But in the case of when your plasma dimension itself is very small, and if you are using these probes, then sometimes it's very challenging also. So because it disturbs a lot, and then the extracted parameters may not be very accurate or reliable. So these kind of techniques I have not seen often used for such kind of a plasma jets. There are one or two studies, but the results are very much questionable in that case also. However, if you look at the spectroscopy based approaches, they are very much popular. And because in spectroscopy, you can actually sometimes do non-invasive way also. So we'll discuss what non-invasive way is. So there are two techniques. You will see that these are very suitable techniques for diagnosing such kind of a plasma, and two approaches which we call active approach. One is we call passive approach. Let's see what this active and passive approach is. So one, the passive approach will comes in the category what I will describe is we call emission spectroscopy, and active approach is what we call absorption spectroscopy. I have tried to include both the methods at some point so that I can give the idea to audience for both. But just to highlight the power of spectroscopy. So as we know, spectroscopy is not a new technique. It has been used since centuries, especially if you notice the development of quantum mechanics or atomic physics, it happens around the spectroscopic method. When Warmer first did the experiments for hydrogen lines, and after that, we have seen the sodium light, and then we start seeing why the splitting happened. And as soon as we notice that there is an improvement in the spectroscopic measurement, that improvement also helped the development of atomic physics, atomic molecular physics, as well as quantum mechanics. So they are very much correlated. Similarly, if we look other fields also like astrophysics, so lots of emissions we are recording that is coming from interstellar bodies or medium, and they is being recorded and then analyzed using various techniques, and we can extract the information. So the spectroscopy is kind of a widely used techniques. I'm not going all those things. Different applications use techniques in a different way, but I'll at least try to give you the idea of this low temperature. So what I mean is, like, if you want to perform the spectroscopy, you need an active medium. So in our case, this active medium is plasma. Then you need some equipment, and this can be the very basic equipment which we learn in our early days is a prism. So if you put a prism, you can basically resolve the components of light. Now of course we need better resolution, so we can use a different device. We have gratings, and there are different types of gratings, but we at least need these two things to perform the spectroscopic measurements. Now, these spectroscopic measurements for today's class, I actually divide in two categories. One is emission-based spectroscopy, one is absorption-based. The idea is very simple, very known to us. So let's say if you have kind of a excitation, this is, let's say, my ground state, and I excite, that excitation can happen any process. The simplest one is electron impact excitation, and your excited state, it cannot stay long, so it will decay, and that we are considering, let's say, spontaneous decay. And when it decays, it will produce some kind of an emission. If I record it through a spectrometer, I will see a line, and the wavelength of this line actually can be noticed by the energy difference between these two labels. I can say delta E equals to hc by lambda, and the central wavelength will be almost the same. So it's actually this transition, or where the photon is emitting. Another way in absorption spectroscopy, what we can say, we can send something kind of continuous source, emission source, let's say halogen lamp. If we just illuminate the medium, the active medium, with some continuous halogen, or there are tungsten spark lamps. So you send the light. Now, what will happen? This is all you can understand is through photo excitation. So you have a ground state. The suitable photon, the suitable energy photon will excite from a lower state to upper state. So what you will notice, every atom has its own energy levels, which you can see as a signature of this. And as the emission you will start seeing some kind of absorption. So this will also a kind of a technique. The basic difference, at least for plasma prospect, is this: the emission spectroscopy is very much linked to the upper state, the excited state, whereas the absorption spectroscopy is very much linked, or can provide you the information of the lower state from which the absorption is happening. So sometimes we need the information for this, especially this absorption technique is very good to estimate the metastable population or ground state population in a given plasma, whereas emission is very much helpful for the upper levels, like distribution of excited state population. So let's start with the emission. So if you record an emission and you see a line, let's say this is a typical line. In this line, what are the parameters? So I can at least notice three parameters. One is central wavelength, this central wavelength. And then there is the broadening, which we define through what we call FWHM. There are other ways also to define, but I'm using FWHM, which stands for full width at Hopf maximum. So I'm taking the full width but at the half maximum steady. And then the third thing is the peak value of this intensity. So these three parameters can provide a big insight of the plasma. So if you are recording and if you are extracting these three parameters, through this, we can actually know a lot of information of plasma parameters. For example, before we go, for example, I just want to highlight that in this case here, I'm using intensity. Generally, we define intensity through emission coefficient, and which is like, the watt per second, per meter square, per steradian kind of a definition. But we can also give this definition in terms of photon meter square per second. So what I'm trying to say, as I mentioned, this is, let's say, my upper state P, this is my lower state, and any emission is happening. So I'm trying to tell you the intensity, and let's say this is a spontaneous emission. So the intensity will depend upon APQ. So the intensity should be proportional to this. And also intensity should be proportional to the atom which radiates this, the excited state population. So with some proportionality constant, we can write the intensity of this line PQ as NP APQ. In a very, it's like kind of a absolute line intensity I'm giving in terms of photons count, because my detector is basically counting the photon. But of course, if you want to convert it in a, let's say, energy unit, then you need to divide, multiply by Sc by lambda, which is the energy of one photon. And you need to also, if you want volume per volume, then you need to divide the steradian and per steradian if you want. So that's how we experimentally, it's better to use this terminology because it's easy to correlate the things. So these are the common modern spectrometers that are commercially available. There are various configurations to design a spectrometers one can do in lab also. I intentionally put this thing so that if someone wants to go this field, the one very good configuration is, or popular one is the Chandy-Turner configuration, which is very kind of easily doable. So you need an entrance slit, and then you need a collimator mirror, and you need a grating. So what is required, you need to do a automation so that, so now what will happen, these rays will be collimated on this grating, and grating will put on a focusing mirror, and then you have a detector here. And this detector could be a photomultiplier tube, could be a CCD, or could be a ICCD, depending upon what kind of application you want. Now, if you turn this grating, so by turning this grating, what you can do, you can basically control which wavelength is coming out from this slit and entering on CCD. So let's say you want to record something from starting from 200 nanometer, and let's say go up to 2400 nanometer, kind of that byte range. Then you need to actually use a grating which can basically suitable for this wavelength range, and then you need to basically have the facility so that the grating can turn and you can focus to different wavelength on the camera or photomultiplier tube, and you can get the intensity. These spectrometers are coming nowadays in a very compact form. Now, one important thing when you actually wants to go for a spectrometer is to see what wavelength range. So if you're planning such a thing to do, then first thing you need to check what is, or you need to decide what is the wavelength you want to use, or what is the wavelength of your interest. Once you have the wavelength of interest, that will help you what is the detector, suitable detector that will work. And then you also, the second important thing is what is the resolution of your optics or this spectrometer. So now how do we obtain this resolution? Actually, how do we calculate the resolution? So it's a well-known thing. So resolution we can define through FWHM. I'll define this resolution through one example so that it will be clear to everyone. What is the consequence of resolution? So one parameter which is affecting the resolution is the grating. So let's say if you are using 1200 groups per annum diffraction grating, and if you move to higher diffraction grating, then yes, your resolution will be higher. And if you might have noticed here, in this case, I'm seeing some line, but it's not resolved. But if you use a higher one, you can easily see that this particular line is composed of two lines. So sometimes this resolution is very important. If you want to utilize both the line emission in your analysis, then you cannot use a unresolved emission, and it may lead to an inaccurate result. So how to calculate the optical resolution? So optical resolution mainly depends upon few factors. So one is, let's say, when you decide your optics, like what we were discussing. So when you decide the optics, then based on your optics, so your detector has some kind of a reason. So depending upon the pixel size. So let's say if you are using, I'm assuming that you are using a linear detector which has 2048 pixels in a row. So you can focus in this reason, this physical length, your frame. Now, what is the frame size depend upon what kind of a focal length you are using in your lens. So let's say I choose 650 nanometer. So when I choose 650 nanometer, I can calculate this frame size, which when I mean 650 nanometer, it means in one frame I can record, let's say, from 200 to 850. If I'm using this, if I reduce this, then I'm lesser. So 650 nanometer, then how much the pixel size here? So I'm thinking, let's say this is 2048. Then you can calculate, for example, for 650 nanometers divided by 2048 pixels. So you are getting something kind of a dispersion value is around 0.32 nanometer per pixel. Now you also need to see what kind of a slit width you have. So each, depending upon your slit width, let's say you choose slit width of 10 micrometer, then this value will becomes, if you multiply, it's almost like 3.2 pixels. So the optical resolution will be this dispersion value and the pixel resolution. So this the final value, let's say we have dispersion is something like 0.32 nanometer per pixel. If I multiply with this 3.2 pixel resolution, then you are getting something for this 10 micrometer slit is 1.902 or 1 nanometer, close to 1 nanometer. So if your line is separated by 1 nanometer length, this kind of a configuration is very suitable. But if not, then you have to change then you need to buy a bigger size spectrometer. More focal length may allow you, but it will reduce your frame size, but it can allow you better resolution. Now there is a calibration also. Before using these spectrometers, we need to perform wavelength and standard calibration. Nowadays standards lamps are available, so one can perform. I'm skipping this part because it's actually not very much interesting. So let me come to the original point where we were in the emission spectroscopy. So I was telling you that there are three parameters, three measurable quantities that we can use to diagnose the plasma. Now the first quantity is what we call the central wavelength. This central wavelength is actually the signature of the element. So if we record, let's say, emission, and then we can know what kind of elemental composition of that material is. So there is very popular technique called laser-induced breakdown spectroscopy. So in this laser, there are different applications. As you can see, there's multiple applications where lips can be applied. But the basic fundamental idea is that we need to know the composition, elemental composition, and that is linked with this central wavelength. So the typical kind of experiment is that you have a sample, then you send some pulsed beam, and this pulsed beam forms a kind of a plasma, which generally we call a laser-induced plasma, and this plasma emit the wave, various emission, and you record that emission. So once you record this emission, then let's say this is a one typical emission that was recorded, and this is a typical setup. So we have, let's say, a ND-arc laser. That depends upon what kind of a power. Different power lasers are also available. This also depends upon what kind of a sample you want to characterize. And then you create a small, very small laser-induced plasma, and then you basically record it through a spectrometer. And then you saw these lines. Now these lines, basically, they are very particular to the energy levels of particular element. And by comparing the theoretical values of these lines with the experimental recorded, you can actually obtain what is the composition inside this element. And it's very commercial technique, has been used a lot. So there is few advantages of this ellipse, like it can apply to any sample, and it's a non-destructive in the sense like we apply the laser to a very specific spot. Laser can be very tuned to a very fine spot. So you're not basically disturbing the whole composition. Where we need a very small emission just to see the elemental composition. But there are limitations also. For example, the measurement accuracy is always a problem, but there is a bigger problem, what we call self-absorption. So self-absorption means if you're sending the beam, if let's say this is a plasma which is created, now before your emission comes, it can get absorbed also inside. And that's what we call self-absorption. Now, because of this self-absorption, what happens? Well, the analysis which you are doing, that may get affected using this laser induced breakdown. For example, if you want to know the temperature of this plasma, then if you don't account the self absorption very accurately, then the results could be could influence, could may not be true. The second approach is what we call this broadening. So as you know, there are various like various mechanisms which created this broadening. One is actually what we call, which is can be present in any unperturbed atoms also, is natural broadening. It's mainly related to the Heisenberg's uncertainty principle. So, which means that this broadening will present no matter what you have the atom, all atoms will have. So we can never have a single point kind of an emission. You'll always have some broaden, at least natural broadening will be present. But whenever you do measurement, there will always be additional broadening, what we call instrumental broadening. Now, beside these broadenings, there is one very popular broadening, which is a Doppler broadening. And then there is a called Lorentzian effects, which comes under the collisional broadening. So collisional broadenings generally arise because of, let's say, if you have some atom and you have charge density surrounding to this. Because of this charge density, what will happen? The emission get influenced like a Stark effect. So energy level will be perturbed, and that perturbation will lead to the broadening of the emission. So if you are having a low pressure plasma, if you're let's say collisional broadening is not very important. Now, how do we know that which kind of a broadening is basically dominant in the plasma? So if you have the first, of course, is Doppler broadening. But besides this Doppler broadening, one can know by fitting these emission lines through some theoretical functions. So one popular function is a Gaussian. So if you have a Doppler broadening, dominant Doppler broadening in your plasma, then what will happen? Your line can be fitted very nicely through a Gaussian profile. However, if you start having contributions from collisional broadening, let's say Stark effect or pressure broadening or resonance broadening, then you will not be able to fit your line through this kind of a Gaussian profile. In that case, these kind of a broadening, which comes under collisional broadening category, they have something kind of a Lorentzian profile. So you need some profile which is a convolution of Gaussian as well as Lorentzian profile. And this profile is actually theoretical profile is called as Bogue function. So as you see, this Bogue function, if I'm defining it through a parameter A, so for A equals to 0, it's like a pure Doppler. But as you introduce more and more, as you can think of it as a more and more collisional broadening is happening, then you will start deviating from Gaussian profile to this kind of because there is an inclusion of Lorentzian profile also in your system. But let's say if I have only Doppler broadening dominant in my plasma, then I can measure the temperature, because the Doppler broadening is is very much linked with the gas temperature. Why? Because if you notice that the average energy of radiating atom, if they're coming closer to the source detector or going away the source, that is what causing the Doppler broadening. So the broadening will be dependent on the average energy of these atoms. So this is very much linked. That is why we can use the Doppler broadening to estimate the gas temperature. So this is a non-invasive technique. I'm not introducing any probe here inside this medium. I'm just recording the emission that is coming from this medium. And by doing this Doppler broadening, I can measure the temperature of this, provided that the Doppler broadening only dominate. If there is a collisional broadening, yes, then we cannot. Then we have to do other techniques. But at least in the case when Doppler broadening is dominant, we can use this technique, non-invasive technique. However, in order to implement that technique, it's not that straightforward, because let's say if I'm saying that this is a Gaussian profile broadening I'm getting, but this Gaussian profile will also, even in the Doppler broadening condition, when I'm avoiding the collision broadening, you will have at least two major contribution apart from natural broadening. I'm considering that as negligible compared to these two. You will have a Doppler broadening, but you will also have a instrumental broadening. So it is very important that before getting the results, you correct it through the instrumental broadening. Now, how do we obtain this instrumental broadening?
Dr. Darshan? Sir? Dr. Reetesh?
Yes, ma'am.
I think sir got disconnected.
Yeah. I am trying to call him.
Okay, sir. Okay.
Okay.
Hello, I'm here only.
Okay, sir.
Okay. I think I'm here only. I was able to hear you also.
Okay, sir.
Okay, so can you see my screen just quickly so I can continue then?
Yes, sir. Yes, sir.
Can you? Okay, so what I was discussing, sorry for this inconvenience. What I was discussing, if you record this emission from a low temperature lamp for which the gas temperature is already known, then you can use the same formula and you can estimate first the instrument broadening and then whatever the known source. So it's like kind of a first getting the reference value and then you can perform to a whatever the medium you have such diagnostic studies. I'm not going to in detail the collision broadening, but collision broadening can also be used. And one very popular technique of collision broadening is using this Stark broadening, especially for hydrogen lines. One can also estimate the electron density in the plasma. It's been used a lot, but I'm skipping that part. Now, the third or the most important thing, if I have a peak value, then also I can know about the plasma parameter. And one very important plasma parameter that we can estimate using this peak value is the electron temperature or average energy of the temperature inside the plasma. Now, how do we do that? So what you need to do, let's do it in a, I will do it in a, actually this is one of the paper we published. So this will be a real kind of a thing. So we have this plasma jet. Then we perform the experiment. So you're seeing that this is a plasma which is coming out. Then we recorded this emission. We have done some optics axis just to not take the emission from full region, but to remain somewhere in the spatial, so that we are not disturbing. We want to do a spatially resolved characterization. We use some irises and some optics, and then we recorded this emission using one spectrometer. Some optical parameter was here. They can be seen in this paper also if somebody is interested, or we can discuss this later. But that's not the idea. What I'm trying to say, let's say I formed the plasma, then I recorded the measurement. Then what you will notice in this measurement, so this is a typical measurement which I saw. So you will see a lot of lines here, and we can actually pinpoint the wavelengths of these. Now these lines, since I'm working with argon, so this is very much natural to see the emission from argon. But beside this, I noticed emission from nitrogen. That is mainly because my one side was open to ambient air, which means the air has nitrogen and oxygen components. So I'm expecting to see some nitrogen emission as well. I think I see 7 line at this oxygen line. And then there was some hydrogen, which is mainly coming from the water vapors present in the air. So the water molecule breaks and can produce kind of a line. Now the condition is I got this emission, and I can also calculate the peak value of these lines, different argon lines. Now, how do I obtain the electron temperature? What is the trick to obtain the electron temperature using these peak values? So in order to do so, this is a typical argon fine structure level. So just to revise the thing, see, we have a ground state, which is 3p6. Then after that, argon has this 3p54s fine structure thing. And either you perform LS or JJ coupling, you will notice that this will have 4 fine structure levels, 2, 1, 0, 1. Normally, in a Paschen notation, we call this as a 1s state also. It's a very popular term. Then if you go and excite one on this electron from 3p6 to 4p, then you will have, we call it 2p in Paschen notation. If you do LS coupling or JJ coupling, you will notice there are 10 fine structure state, various J values. And the emission which I'm seeing is actually coming from these two, the transition between these two excited levels. So when the excited spontaneous decay happens from this level to this level, all the lines which I'm seeing is coming from this. So in fact, in this matrix, I have shown all. So theoretically, if I do this, what we call the selection rule, optical selection rule, delta J, comma 0 plus 1 and 0 to 0 is not allowed, or LS coupling way. Then if I listed theoretically all the lines, I will notice all this line, but all the lines are not that strong. So in your experiment, you may not be able to see all the lines, expected lines, but at least some intense line is expected to see. So in a plasma jet, the emission was basically dominated by transition between these two manifolds. Now, your life is very easy if you have a local thermal equilibrium, because the intensity, peak intensity, theoretically can be defined as the population of the excited state. In this case, these are the excited states, and the spontaneous decay coefficient. So which means if you have a LTE condition, then the population of this excited state can be given through some thermodynamic equilibrium relation, which is in this case Boltzmann, because we are talking about a neutral excitation here. So this, we don't need any model, nothing. We have already the expression, equilibrium expression. We can calculate this. And how do I know that whether it's working? So what we can do, the trick is we can plot what we call Boltzmann plot. So this Boltzmann plot will have, let's say, this kind of a deviation here. If it's fitting very nicely with the straight line, then yes, then you can say, okay, local thermal equilibrium exists, and you can use right away, and life is easy. However, in all, at least not all, most of the plasmas, we have a strong non-equilibrium. For example, in this case, you notice that the straight line fitting is not very much possible. It's deviating significantly. So in those cases, we need to use some population kinetic models, and there are various models available. The one which I will be talking about is the collision radiative model. This is a generalized model in the sense we don't consider any equilibrium. We manually consider the processes. So in this particular case, let me explain this through you one example. So in this particular case, when I was studying this argon plasma and I noticed that my emission is not, so I need to consider all the process. So what process? This is where your challenge comes, and you need to do it multiple times to optimize your model. So first process, we use the excitation, de-excitation of electrons. We use from ground state as well as excited state. Then we also consider the de-excitation, which means electron can de-excite the state also from this. Then we have considered the contribution from higher lying states. This is kind of a through some cross section. I'll tell you how we calculate this. And then we also calculate the transitions between among these levels and the decay, the spontaneous decay and quenching. So all these process, when you take these process, you can basically write the population distribution for each individual levels. I'm sorry, I'm going a little bit fast, but if anybody is interested, I will be answering the questions later on. The idea is if you let's say I have an electron impact excitation process and you want to include this process in the model, then you need to calculate the rate coefficient. And in order to calculate the rate coefficient, you need corresponding cross section which define the probability of this process, and you need to integrate this process with some distribution, because your plasma medium doesn't have a single electron energy. It is actually having some distribution. It could be Maxwellian, it could be non-Maxwellian. So you need to perform the integration. So of course, the non-zero will be only where the overlap will happen. So even if I say 1 electron volt plasma, the average electron energy is 1 electron volt, but this 1 electron volt plasma can also excite the state, let's say make the excitation which has a 11 electron volt or so, kind of a difference, because you have a distribution. So there will always be a tail, Maxwellian tail, which have the sufficient threshold energy, however very small compared to the other, but there is always possibility to have such excitation. This is just a caution. If someone wants to do such things, then you should be very careful in using the cross sections. There are various databases available. One can choose. We also do cross section calculation. That is a different thing. So I'm avoiding this. What is required now? Once you solve those equations, like you have developed the model, then model gives you the population of excited state, and you take these excited state population, multiply with Aij, the suitable spontaneous that will give you the model population. You have this intensity also from the measurement. Then we need to calculate the deviation. This deviation, if you plot, most of the times, if your model is good enough, then you will notice some kind of a minimum deviation, or like where the agreement is best. And this is the point where your model intensity matches with the, or closely matches with the measurements. That is the point corresponding to those points. So let's say in this case, I will consider 1.7 electron volt is my plasma temperature. So using this technique, one can easily, of course, model development is a tricky task, but still in many cases, the model may not be very tricky. So you can estimate the electron temperature. And then I will skip few things, but I will want to tell you the absorption spectroscopy. So the main idea about absorption spectroscopy is, this is what we discussed the emission. So main idea is absorption spectroscopy is you have an absorbing medium. You need a light source. Now, there are two possibilities in light source. You can use a white light source, which I'm saying as a continuous light source. Nowadays, people are using laser also. Laser is much better device to do absorption spectroscopy. Of course, it costs more. So because when you use laser, this is more spatially resolved thing, because laser, the divergence of laser is much lesser compared to a white light source. So your diagnostic will be much more accurate. So in these absorption technique, the idea is like we can start with a simple defining the intensity, and depending upon this is a length absorption, medium length, and this is basically absorption coefficient. So you can simply define how the light is being absorbed by this medium. Based on this values, one can also calculate what is the population of lower level. In fact, one can do much better. So for example, in one case, in this, what is required experimentally, what we need to do experimentally is to find this absorption coefficient AL. How we define AL? So let's say I perform 3 measurement. In one measurement, which is I'm calling as P plus L, both the lamp and the plasma were on. Then in one measurement, only plasma was there. And in one measurement, only lamp was there. And of course, I corrected through background. So what if my I P plus L, plasma plus lamp measurement is almost equals to plasma 1? So which means there is like all the emission were absorbed here. So because in the case of P plus L and in the case of plasma, if they are same, then what I'm trying to say that whatever emission you send to the medium, everything was absorbed by this absorbing medium. So let's say this absorbing medium, you send some signal with some reference intensity and everything was absorbed along this path, then it is expected that these two will be equal. And if you put this value, then what you will get like AL as 1, unity. The other case is like if there is no absorption at all happens, in that case, what will happen, this plasma plus P plus L is almost equals to the IL. So, and the second case, P plus L will be almost equals to IL, and since plasma is not absorbing, so the intensity will be almost 0. And in this case, you will notice that your absorption coefficient is almost 0, which means there are no absorbing atoms are present in this. And this is a very popular technique. So let me give you one example and then we can, this is what I was trying to say. Let's say if you have a white light absorption and you have two close by lines, you notice that they are so much overlap that you don't know whether you're recording the absorption from this or this, because there may be the interference also, influence from one to another. However, if you use laser absorption, you can tune it very nicely. Like laser is very precise. So you can do precision spectroscopy using the laser. This one thing which I want to tell, then I'll close. The idea in absorption spectroscopy is very simple. You have some absorbing medium, you have a source, then you can record. So we discussed this absorption, but this is not the one form of the spectroscopy. You can also record at a perpendicular the emission. And there is actually two popular. Fluorescence is more popular, but there are two popular like techniques. One we call fluorescence technique, another one is phosphorescence technique. So in this, you excite the laser with some wavelength, and then you record not on the same line of sight, but at a perpendicular, so that you kill the main emission. So if you do that, then you can also record the fluorescence. Now, how we distinguish between phosphorescence and fluorescence, it can be seen from this figure. Like it depends upon how the processes are happening inside. So let's say if you excite, the phenomena is same. Like this figure is actually defining all the three processes in the same way. The time scale is of course different. So you are absorbing some length. Then there is a possibility of internal and vibrational relaxation. And then you basically get some kind of a fluorescence here. Emission. Now, if there is an inter-system crossing, let's say if this is what you get from here, if there is an inter-system crossing and then there is a relaxation, then you get some signal, then it's phosphorescence. The choice for phosphorescence is slightly tricky because it's a slow process. It is a very high time scale. So many of the times people want to use fluorescence because it's a faster process. You can record the dynamics in a much faster way, and you can see the process time evolution of processes also. You can see chemical pathways also. Now this is again the same thing. These process in terms of plasma, they are being used to do radical characterization. So one of the most important radical we have is what we call OH radicals. The reason why it's more important because its oxidization potential is very, very high. It is among the all other radicals, it has highest oxidation potential. So if you, let's say if you have produced a plasma and you ensure the non-thermal nature, and you want to ensure the optimized or highest processing through that plasma, keeping the non-thermal, then you have to record or you have to monitor at least the generation of this radical. If you are still effectively generating this radical, then yes, your plasma will be in non-thermal also, as well it will be also giving you very accurate result, a kind of a processing. So how we can do that? So let's say we can use this fluorescence, UV visible fluorescence steam. So you need some agent, chemical agent. So very popular agent for OH radicals is what we call this TPA. So this TPA is very much active with this OH radical. This is a very fast reaction. You need an agent. So you mix, so then you apply the plasma. Now you need the agent so that as soon as OH radicals produces, it get interacts and forms to another component. So this component has a reaction, very fast reaction with OH radicals and form another, which we call common name is HTPA. Now this particular molecule has an excitation at 350 nanometer. So it can absorb this 315 nanometer wavelength, and it also have a emission, which we say fluorescence, as 421. So we can record this 421. So for example, here in this graph, what I'm showing you, as a time varying. So the measurement was recorded at 2, 4, 6, 8, 10, 12, 14, while the plasma was operating. And you can notice that, yes, there is a greater OH radical production. So by monitoring this OH radical production, you can also know what is the efficiency of your process and what is the best parameter for a particular application. So with this, I'm almost reaching to the conclusion. So what I'm trying to tell you in this lecture is that emission and absorption spectroscopy, they are very much powerful, efficient, effective, but they too have limitations also. The limitations is sometimes you need, in order to have a spatial and temporal measurement, you need to put a lot of optics beside your, let's say, plasma or any other medium, which is a challenging task. For example, any place, if you're recording, let's say this is a source and you're recording through an optical fiber, then you always record something which is in the field of view. So spatial distribution is always challenging. But with the use of laser and other things, such things can be, up to some part, we can compensate this, and we can still use the spectroscopy. So with this, I would like to conclude my session. And if there are any questions, I would be happy to take. I would also like to mention my research group. These are the students who are working with me at present. Thank you.